Hey everybody. I wanted to make a quick video to discuss analyzing the third data set. That was the one in your experiment that you actually had to linearize before you could write an equation for it. The other ones actually looked really good when I looked at all of your stuff. Some of you struggled with this one. Here goes, and I'm just simply doing the process that was in the reading. I think some of the people who are struggling aren't struggling so much because they couldn't understand the process, but because they won't read or watch any of the videos, and that, well, I can't really fix that part. But if you are willing to watch, then you're watching this, and here goes. The question was, and you're supposed to state the question you're trying to answer. What is the relationship, if any, between the period of oscillation for a spring and the mass on the end? I just have a quick description here. Use a stopwatch to find the period for different mass values. Here's the mass on the end of the spring. Period is the time it takes for one full trip to occur, one full bounce. So up and back down is one period. I have notes over here. Time 10 periods and divide by 10 to get accurate value for one period. In particular, with the lighter masses, which oscillate very quickly, it's hard to get one period timed. So press go when it's at the bottom. 1, 2, 3, 4, 5, 6, 7, 8, 9. Stop when it gets to the bottom on the 10th time. And then just divide by 10. Easy peasy. And then do multiple trials and average. I chose to do 3 trials for each different mass. Mass is measured in grams, periods measured in seconds. These are just notes. So here's the data that I gathered. 50 grams is very hard to time. I'll grant you that. One great idea, I think it was Tyler Reich said, slow the video down to quarter speed and time it, and then just divide by 4. That's a great idea, and I did try it, and it turns out to work very well. So if you didn't do that, not a big deal. Hopefully you got something around this time. The average, so twice the mass, notice does not double the period. So I don't think these two things are proportional. 50 to 200 grams, that would be 4 times the mass. Certainly is not 4 times the period. Now 50 to 800, that's 16 times the mass. Definitely not 16 times the period. So I plotted, forget about this last column for right now, that was added later. I plotted period versus mass. So took my data, my period values went here. I went from 0 up to 1.5, which would allow me to put all of my values in. And then mass, I had to go from 0 to 800. So 0 all the way up to 800. Big mistake that I saw. Just because I went 50, 100, 200, 400, 800 when I did the trials, that doesn't mean that you can say 0, 50, 100, 200, 400, 800. You have to go up by even amounts each time. So this is how I chose to space my axis out. You've got to keep it consistent. You always want to include the origin in your graph as well. Don't put any breaks or any silliness like that in there. So here's what it looks like. Clearly it is a sideways opening parabola if you look at it. So since it's a sideways opening parabola, what you should probably do, you have to linearize this before you can write an equation for it. You can't write an equation for a curve. Since the period values are not keeping up with the mass values, as the mass increases, the period does not increase accordingly. A way to linearize this is to square whatever is on this axis to make these values grow more quickly. So I did that. That's where this extra column came from. So I took all of my period values, which are measured in seconds, and I squared every one of them, and now the units are seconds squared. So 0.366 seconds squared is 0.134 square seconds. 0.476 times 0.476 is 0.221, and the units are seconds squared. I literally just squared everything in here to make this column. That's where the next plot comes in. This is called a test plot, if you did your reading. What I plotted was period squared, so this column, versus mass, this column. When I do that, I get a nice linear trend here. I did get a really small intercept. If you've been watching any of the videos you've been assigned, you're supposed to figure out whether or not this is a negligible intercept or not. Negligible meaning you could just ignore it, it's tiny. Well, my intercept is about 0.03, just reading it from the graph. And if it's less than 5% of the maximum value on this axis, you can ignore it. It's probably negligible. So 5% of this value is a lot more than 0.03. It's over double. So I'm just going to ignore this. So my analysis, first, define your variables. I'm calling period T. I'm calling mass M. This is any line that comes from the origin. Like I said, my intercept is negligible. I can ignore it. But when I don't have a y-axis, look what I have. I have a period squared axis. So I'm not going to write y. I'm going to write t squared, period squared. K is what we use for the slope. And here's why. Because we often use m for mass. I don't have an x-axis. I have a mass axis. So y equals kx turns into t squared equals km. Period squared, mass, slope. Got to find the slope. So rise over run, change in t squared. It's the change in this axis divided by the change in mass. That's this axis. I picked 2 points, and you got to label them. 2 points that actually do sit on my line. They don't have to be measured points, but I chose these two because I already knew their values. They were measured, and they did sit on the line. So when I subtract my t squared values, so that one was 1.42 minus 0.134. That's my change in t squared. That's the rise. The run is 800 grams minus 50 grams. So 800 grams minus 50 grams. Works out to be, and the units are kind of critical here, 0.0017 seconds squared per gram. This is just my slope. So the final equation, plugging my slope that I just found in, is t squared equals the slope times m. And this is simply the equation you get from plugging in the variable names and the slope into this generic equation at the beginning. Now, a good way to test this is to take one of your mass values, plug it in, do the math, and solve for the period. And that's what we're going to try out in class today. In fact, we're going to try a new mass that you've never even tested to see how well the equations work. This is pretty close to what a lot of you got for the slope, so I think you'll get good results.